Okay, so by popular demand, we are doing the lesson 4 video for chapter 5, polynomials. So this is still part of the intro section. This is the last little bit before your quiz next week. So the first example is asking you to write the tiles, or pardon me, draw the tiles or write the expression that goes with the tiles. I'm not going to do this for you. You can do this and double check it. Just keep in mind, for every shape, different set of shapes, you should have a different term. Okay, so the next part asks you to make models of each polynomial. So I want you to build them, and when you build them, you should get two groups that look very similar, right? They both have 2 green x squareds, they both have 3 negative x's, and they both have 5 negative 1's. So they're the exact same polynomial. They just are written in different order. So this is written in standard form. So we're going from highest exponent to lower exponent to no exponent. We want to write our expressions in standard form. Whoops. And the second example is not in standard form. It's technically not incorrect, but it's not as correct as it should be. And so these two sets of polynomials, or these two expressions, pardon me, are actually equal. And so is there a third way? Well, there are many other ways that we could write this polynomial, just by changing the order. So maybe we go negative 3x plus 2x squared minus 5, or negative 3x minus 5 plus 2x squared. Anyway, we can switch them around. What I want you to keep in mind, though, is that the sign is following the term. Whatever is negative and whatever is positive isn't switching. The x squared is always staying positive, and the x and the constant are always staying negative. So then we could write equivalent expressions for these terms as well. And an equivalent expression is just another expression that has the same terms but in a different order. So there's our first term, our second term, our third term. Just switch around the order, and you get equivalent expressions. So equivalent means equal value, and their expressions. Okay, so 2 different expressions that have the same value. I won't do the other 2 examples. I think you get the idea. If you want to check them with me tomorrow, you can. Okay, going from an expression into words. This, for some reason, you are very not good at. I blame your elementary teachers, except for Miss Wobbly, but I blame the rest. And so anyways, the first one says we have n plus 3. I don't want you to just write n plus 3. Okay, that's what you did when you were in grade 3. We're going to step it up a bit from there. So you might want to say a number increased by 3. Or 3 more than a number, or 3 more than an age, or whatever. And then we would say that n equals a number. So we're saying what variable we're using and what is it standing for. Same thing for the second one, 2x minus 3. So we're going to say x is standing in for a number. And so 2x, we could say 2 times or twice. So say twice a number. And then for the minus 3 part, we're not going to say minus 3. Maybe we could say twice a number decreased by 3. Or we could say 3 less. Just kidding. 3 less than twice a number. So the words don't always have to be in the same order as the expression. Just because 2x comes first doesn't mean it necessarily comes first when we put it in words. Okay, and then the third one, I will let you try something for that one on your own, but make sure that you're identifying what B stands for. Okay, so now this one is jumping ahead a little bit. When we start to talk about the length and width of the rectangle made by algebra tiles, I talked with at least one of the classes about this, so it's not entirely new to all of you. And we will be looking at this in Chapter 7 as well, but I wanted to sort of mention it now. If this doesn't make a ton of sense, we'll make sure we take some time in class together. But basically what's happening is the algebra tiles are representing the area of a rectangle. And so we want to look at what the length and the width are if this was our rectangle. So this rectangle has an area of x squared plus 2x. Okay, so then we're going to look at, well, what length and width made that rectangle. And if we think of what we've done already with rectangles, if we say an area is 10, well, the lengths are probably 2 and 5 or 1 and 10 or something like that. Two numbers that multiply to make the area. So we're thinking the same thing with algebra tiles. And so we look at and say, well, what is the length? Well, that is a length of x because it's an x tile. So then let's look at the width. We have a length of x, and then we have a length of 1, and we have a length of 1. So on the width side, we could say that we have x plus 2, 1 plus 1, right? So x times x plus 2, and I'm going to put it in brackets so we know that it has to get times by everything, equals x squared plus 2x. Okay, try that again on the second one. So again, we're looking at the area of the rectangle being represented by the tiles. So we have 2x squared plus 3x for the area. And then for the length and width, we have a length of x. And we have a width of x, and 1, and 1, and 1. So 2x plus 3. Now notice we're only looking at the side lengths. We're not paying attention to what tile is there. We're just looking at the edge lengths to find the length and width. So on this one we have x times 2x plus 3 gives us 2x squared plus 3x. And we can only line up sides together that actually have the same value. I can't take a ones tile. Now this one's going to be way too big, but let's just do this. Right? My ones tiles don't line up with the edge. We did that already. We tried that in class, and it was 5 point something. But none of you were willing to bet anything for exactly what that decimal place was. So we can't line up ones. We can only line up one with the end. So here, let's see if I can make it the same size. Okay, so we could line up ones there because the length's the same, but I couldn't line up ones along this side because we don't know the exact value. It's a variable. So just to kind of give you an idea for that. Okay, so we're hosting a fundraiser at the school, which is actually true. We actually are. However, the tickets are not being sold for the picnic. They are being sold for Literacy Mountain. Anyways, in this example, tickets are sold for a school picnic. Students and parents are invited. So, students' tickets cost $5, and parent tickets are $10. Obviously, we're going to charge your parents more because, you know, we can. So we need to come up with an expression that represents the amount of money raised by the school. So we're going to have two different variables, right? Because we're going to have some amount of student tickets. So let's say that we're going to use S to stand for student tickets. And then we have parent tickets. So let's have P stand for parent tickets. Okay? And so, and then whatever the student ticket, oops, wrong letter. Oh my goodness. So the student tickets plus the parent tickets is going to equal the total amount of money that they make. But right now, this is assuming that the student tickets and parent tickets each cost $1 each. And so student tickets are going to cost 5S. So if we sold 10 student tickets, 5 times 10 would make $50. And parent tickets cost $10. So for each parent ticket we sell, we're going to make $10. So if we sell 10 of them, we would make $100. 10 times 10. So now we're saying, okay, well, we know that 75 students went. So that's our S value. And 90 parents went. That's our P value. So we want to know what do we earn? So 5S plus 10P. So 5 times the student tickets, which was 75, plus 10 times the parent tickets, which was 90. Keeping in mind our order of operations, we're going to multiply before we add. And we get 375 plus 900 equals $1,275 made at the picnic. No. Yeah. Okay. So I hope that will help you for lesson 4. Notice there are quite a few practice questions there. I'm going to say choose 5. Okay? I know, I'm too nice. Okay, and that's it for your lesson 4 video. Next up, you have a quiz.